Today we will discuss about chapter number 1, chemical kinetics. Introduction. Chemical kinetics is the branch of chemistry which deal with the rate of a chemical reaction, the factor which affect the reaction rate and the mechanism by which these reactions occur. In other words, chemical kinetics tell about how fast a particular reaction takes place and what mechanism it follows. Also, it tells us how the reaction rate is dependent on a variable like temperature, pressure, and concentration of reacting species, etc. The chemical reaction can be classified into following categories on the basis of their speed. Instantaneous reaction which occur at very fast speed. These reactions occur as soon as the reactants are mixed and is practically not possible to measure the speed of a such reaction by ordinary method. Such reaction include several ionic reaction, neutralization reaction of acid and base, etc. Example are AgNO3 plus NaCl give AgCl3 PPT plus NaNO3 aqueous. Sodium hydroxide plus HCl give NaOH plus H2O. Second, extremely slow reaction which proceed at very slow speed for the rusting of iron, combination of hydrogen and oxygen at ordinary temperature, etc. These reactions occur at slow speed that is not possible to determine the rate of reaction. Third, reaction which proceed at measurable speed. These are a chemical reaction which proceed at moderate speed which can be easily measured. Some example of such type of reaction are hydrolysis of ether, ethyl acetate plus water in the presence of acid give acetic acid plus ethyl alcohol. Inversion of a sugarcane. Sugarcane plus water in the presence of acid give glucose and fructose. Decomposition of HI. 2HI give H2 plus I2. Different chemical reaction proceed at different rate. An obvious reason for this is that a chemical reaction involves breaking of bond in the reactant and the formation of a new bond in the product. The energy required and for breaking of bond and energy evolved for bond formation is different from different reaction. That is why different reaction proceed at different rate. The instantaneous involve just combine of ions that are already present in the solution. Hence, these reactions occur at very fast rate. The reaction which measurable rate are the focus of attention in the chemical kinetics. The chemical kinetics is converted with the following accepts. First, the rate of reaction and the rate laws. Second, what is the effect of temperature, pressure, concentration, and catalyst on the rate of a reaction? Third, what is the mechanism or the sequence of a step by which the rate reaction occurs? Rate of a chemical reaction. The rate of a chemical reaction or the reacting velocity may be defined as the change in the concentration of any of the reactant or the product per unit time. For example, consider a simple reaction A change into B. Thus, rate of reaction decrease in concentration of A divided by time taken is equal to increase in concentration of B divided by time taken. Unit of a rate of a reaction. Rate of a reaction has been of a concentration divided by time. The concentration is usually expressed in mole per liter. For gaseous reactant, instead of concentration we take place in atmospheric and time may be expressed in second, minute and hour. Therefore, the unit of reaction rate are as follows: mole per liter per second or mole dm cube per second or mole liter per second. Mole dm cube per second, mole liter per minute or mole per liter per minute, mole per liter per hour. For gaseous reactant or a product, the concentration term is expressed in the term of a partial pressure. Therefore, the unit of rate of reaction will be atmosphere per second or atmosphere per minute or atmosphere per hour. The molar concentration of reactant and the product keep on changing with the time. Therefore, the rate of reaction is not uniform throughout but cap or varying. Therefore, it is the most appropriate to express the rate of reaction at a particular instant time. Such a reaction called instantaneous rate of reaction and is defined as the change for the concentration of any one of the reactant or a product at a particular instant of a time. Expressing the instantaneous rate of reaction. According to law of mass action, the rate reaction depends upon the molar concentration of a reactant. As the concentration of a reactant change with the time, so the rate of reaction also change with the time. Therefore, it is more applicable to express the rate of reaction at a particular instant of a time. To express the rate of reaction, a small interval of a time dt is taken and it is assumed that the rate of reaction remains constant in interval of a time. If dx is the small change in concentration of any of a reactant or the product, then the rate of reaction is expressed as rate of reaction is equal to dx by dt. In case of reactant, concentration decreases with the time. Therefore, a negative sign is put before dx by dt, such that minus dx by dt. On the other hand, the concentration of a product increases with time, and hence a positive sign is taken before dx by dt, such that plus dx by dt. Consider the following reaction: A plus B change into L plus M. The rate of reaction such is expressed in terms of a following of a concentration of a reactant or increase in the concentration of a product. Thus, the rate of reaction based on the rate of a concentration of a of each species is taken as rate of reaction dx by dt is equal to minus dA by dt is equal to minus dB by dt is equal to plus dL by dt plus dm by dt. May be symbolized that the rate of reaction is always positive. The negative sign is above expressed indicate the fall in the concentration of reaction phase. The positive sign is the expression to indicate the increase in the concentration of product with the passage of time. Here dA and dB represent the small decrease in concentration of A and B, and dL and dm represent the small increase in the concentration of a product L and M. For a general reaction, A coefficient of A plus coefficient of B change into coefficient of L plus coefficient of M. The rate of reaction is written as the following: rate of reaction dx by dt is equal to 1 minus 1 by A dA by dt is equal to minus 1 by coefficient of B dB by dt is equal to plus 1 by L dL by dt is equal to plus 1 by M dM by dt, where A, B, L, M are the stoichiometric coefficient. Measuring the rate of a reaction. The rate of a reaction can be measured by plotting a graph between the concentration of any of the two reactant as a function of a time. The concentration of any of a reactant or the product is measured at a different interval of time. For this, it is necessary that all the other variable except concentration which may affect the rate remain constant. Usually a reaction is carried out and a small amount of a reaction measured is withdrawn at a small interval of a time. This reaction mix is cooled at to a temperature below 0 degrees Celsius by keeping it in a freezing mixture. By doing so, the reaction is arrested such that no further reaction takes place. Now, the concentration of any of the reactant or the product is determined by a suitable method, usually titration, etc. After determining the concentration of a reactant or a product, a concentration term curve is plotted as shown in figure 1. It is not always required to stop the reaction for measuring the concentration of any species at variable time interval. The same information can be observed by noting the change in observable property like change in color, change in pH, volume, pressure, optical rotation with time. According, the graph are plotted to calculate the rate of reaction. All these methods will be taken up as we proceed in the chapter. However, if change in concentration of a reactant or a product is measured with the time, then the rate of a reaction is determined as follows. Curve in figure 1, A and B shown the variation in concentration of a reactant with respect to time. Figure 1c, the change in concentration of product with respect to time. In such type of concentration time curve, the rate of reaction is determined by two methods. First, the rate of reaction by any instant of a time can be determined by the drawing tangent to the concentration term curve at the particular instant. The slope of a tangent then gives the required rate of reaction at that instant. The slope of a curve is equal to tan theta OA by OB is equal to del x by del t is equal to dx by dt. Second, a small change in concentration dx in a small interval of time dt is not directly from the concentration time curve. Assume that the rate of reaction remains constant during the small interval of time. The quantity dx by dt gives the required rate. Figure 1c show the increase in concentration of product with respect to time. The rate of reaction can be determined by drawing the tangent to the curve of a given instant of time or the reading directly the value of dx and dt from the curve. Factor affecting the rate of reaction. The rate of reaction is influenced by the following factor. First, nature of a reactant. Second, concentration of a reactant. Third, temperature of a system. Fourth, presence of a catalyst. Fifth, exposure of a radiation. Sixth, nature of a solvent. For reaction in heterogeneous system in which a reactant is in solid form, the surface area of a reactant also become an important factor affecting the rate of a reaction. By studying these factors which affect the rate reaction, it becomes possible to control the rate of a reaction. First, nature of a reactant. Substance differ in activity and hence in the rate at which they react with other substances. For example, active metal displace hydrogen rapidly and variously from acid, while the less active metal react slowly. Hence, the rate of reaction are also affected by the nature of a reactant. For example, clearly show this effect. First, oxidation of nitric acid oxide and carbon monoxide in air. Nitric oxide plus oxygen give nitrogen. NO2. First, carbon monoxide plus oxygen give carbon dioxide. So, above two reactions seem identical. These are same number of mole of reactant and product in both the cases, and both are oxidation reaction, but they differ in their rate reaction. The reaction is that the nature of a reaction such that NO and CO must be differ. Hence, there is a difference in a rate of a reaction. Second, combustion of chlorine and bromine with hydrogen. Both these reactions are similar as shown ahead. Chlorine plus hydrogen give 2HCl fast. Bromine plus hydrogen give 2HBr slow. Under similar condition, the first reaction is fast while the second is slow. The difference in rate of a reaction can be attributed of the nature of a halogen Cl2 and Br2. So rate of a reaction are influenced by the nature of a reactant. A chemical reaction involving the breaking of old bond and formation of a new bond. The reactivity of a substance is therefore related to the case with which the specific bonds are broken and the number of such bonds involved. As the amount of energy required to break the bond is different in different reactions, hence the rate of reaction also vary with the time of a reactant. Second, concentration of a reactant. It has been observed that the rate of a chemical reaction kept on decreasing with the time. The concentration of a reactant is maximum at the starting of a reactant, and therefore the rate of a reaction of a concentration is also maximum. As the concentration of a reactant decreases, it brings about the corresponding decrease in the rate of reaction. This clearly indicates that the rate of reaction is directly proportional to the concentration of a reactant. The change of a concentration of reactant and therefore the rate of reaction with the time is shown in figure 2. For above figure, it is clear that at the starting of a reaction, the rate of a reaction is large and it decreases with the passage of a time. Therefore, to increase the rate of reaction, we should increase the concentration of one of the one of all of the reactant. In a gaseous phase reaction, the increase in the pressure of a reactant gas increase the rate of a reaction. With increase in pressure, the number of a mole per unit volume increase and therefore rate of a reaction increase. The effect of concentration of a reactant on the reaction rate may be explained in terms of a collision theory. According to collision theory, the rate for a reaction depending on the number of collision per unit between the reactant molecule. By increasing the concentration of one or all the reactant, the number of collision increase and it lead to an increase in the rate of a reaction. Third, temperature of the system. In generally, an increase in temperature increase the rate of almost all chemical reaction. Besides increasing the rate of a reaction, in case it is observed that temperature can initiated the reaction. For example, hydrogen and oxygen do not react at room temperature but react readily to form water when electric spark is passes through them. The rate of all chemical reaction increase with increase in temperature. A generally appropriate rule is that the rate of most of a chemical reaction become double or even triple for every 10% a 10-degree rise in a temperature. This is also called temperature coefficient, which is depend as the ratio of a rate of a constant of a reaction at two temperature differing by 10 degrees Celsius. Thus, temperature coefficient is equal to rate constant T temperature plus 10 degrees Celsius divided by rate constant T degree Celsius is equal to K T plus 10 divided by KT is equal to 2 or 3, where KT plus 10 are the specific rate constant at T degree Celsius and T plus 10 degree Celsius respectively. For example, the temperature coefficient K398 divided by K298 for the saponification reaction or ethyl acetate or with the sodium hydroxide is 1.78, whereas the value of a temperature coefficient for the reaction between the methyl iodide and sodium ethoxide in the solution is approximately 2.9, etc. The marked effect of temperature on the reaction rate can be explained in terms of a number of a collision between the reacting molecule. The increase in temperature will increase in the number of a collision and the rate of reaction increase. But an increase in temperature by 10 degrees Celsius increase in number of a collision by about 2%. This fact is unable to explain the 2 or 3-fold increase in reaction rate for rising every 10 degrees Celsius rise in temperature. Explanation of effect of a temperature on rate of a reaction. The increase in rate of a reaction with increase in temperature is explained on the basis of a collision theory. According to this collision theory, the chemical reaction occurs as a result of a collision between the reacting molecules. However, all collisions do not react in a chemically reaction. Only effective collision between the reactant molecule result in the formation of a product. According to collision theory, only a small fraction of a collision is effectively in bringing about the chemical reaction and the rest of a collision are ineffective. For an ineffective collision, the colliding molecule must have more than or equal to a certain minimum amount of energy called threshold energy. Thus, the threshold energy may be defined as the minimum energy which must be possessed by the colliding molecule to cause a chemical reaction or a collision between them. If the energy of a reacting molecule is less than the value, collision will be ineffective. All the molecules in a substance do not possess the same energy. Thus, there is a distribution of energy among the reacting molecule. If the energy of molecule are plotted against the corresponding fraction of a molecule at a particular temperature, a curve of a type shown in figure 3a is obtained. This is called Maxwell distribution of energy. In the figure 3a, E corresponding to the minimum or threshold energy required for causing effective collision. The molecule having energy equal to or greater than E will be result in formation of a product. To explain the effect of increase in temperature on the number of effective collision, consider the energy distribution of a molecule at two different temperatures T1 and T2, where T2 is equal to T1 plus 10 degrees Celsius. It is evident from the figure 3b that when the temperature is increased from T1 to T2, the curve gets shifted toward right, indicate the number of a molecule with higher energy has increased. The shaded area A, B, E, F at temperature T2 is almost twice as large as shaded area A, B, C, D at temperature T1. Therefore, the fraction of a molecule possess activation energy has increased approximately 2 times for a rise over 10 degrees Celsius in a temperature. Since the rate of reaction depending upon the number of a molecule which possess energy larger than activation energy. Therefore, we may conclude that the rate of a reaction become almost double for every 10 degree rise of a temperature. Concept of activation energy barrier. Familiar reactions such as the burning of coal in air, combination of hydrogen and oxygen gas do not occur unless some extra energy in one form or the other is applied to them. This is because in such reaction the reactant molecule do not possess energy equal to or greater than the threshold energy under normal conditions. So there is no reaction. Thus, some extra energy has to be applied to the reactant to bring their energy equal to threshold energy. Then the reaction starts. The excess energy which may be supplied to the reactant so that their energy become equal to threshold energy is called activation energy EA. It is equal to or difference between the threshold energy for the reaction and the energy possessed by all the reacting molecules. That is, activation energy is equal to threshold energy minus energy possessed by a reacting molecule. This is shown graphically in figure 4 that for a reaction to occur, the colliding molecule has to be absorb some energy and cross the activation energy barrier. When the collider molecule possesses energy equal to EA, an intermediate activated complex is formed, which is different from the reaction as well as the product. Consider a different reaction A2 plus B2 give to AB. The reaction has energy ER. The reaction cannot occur until the colliding molecule A2B2 has sufficient energy equal to threshold energy ET to form an activated complex. In the activated complex, the AA and BB bond are breaking and AB bond are forming as shown. The activation energy complex has a very short lifespan and split into product. Activation energy has an important role in comparing the rate of reaction. As already discussed, the oxidation of NO is a fast reaction, whereas that of a CO is a slow reaction. NO plus half oxygen give NO2 fast. Carbon monoxide plus half oxygen give carbon dioxide slow. In the rate of a case of NO, the activation energy is small, thus only a small increase in energy enables reacting species to cross the energy barrier to form NO2. Therefore, the reaction is fast at room temperature. However, in case of oxidation of a CO, the activation energy is high, so large amount of energy is required by reactant to cross the activation barrier. Hence, the reaction is slow at room temperature. Thus, we conclude that if activation energy is low, the reaction is fast, and if the activation energy is high, the reaction will be slow. The medical relationship between the rate reaction and temperature is given as rate of reaction is equal to Z e to the power minus EA by RT, where Z is the collision frequency of a binary collision and the factor E minus E की power minus EA by RT represent the fraction of a molecule which has energy greater than activation energy EA. For a reaction involving simple molecule, the rate of reaction can be proceed by the equation, but for complicated molecule, the value of a reaction rate are found to be less than those calculated by using above equation. This is because in such reaction, the rate of reaction not only depend on orientation at the time of a collision. Hence, an addition factor P called possibility factor or a steric factor is inserted in above expression. The rate of reaction is equal to P Z e की power minus EA by RT. The value of P varies from unity to above about 10 raised power minus 8 depending upon the nature of a reactant. Presence of a catalyst. A catalyst is a substance which increases the rate of a chemical reaction and can be recovered chemically unchanged at the end of a reaction. For example, manganese dioxide speeds up the thermal decomposition of a potassium chlorate. Magnesium dioxide acts as a catalyst in this reaction and can be recovered unchanged at the end of a reaction. The catalyst provides an entire new path for the reaction in which the reactants are covered to produce quickly. As shown in figure 5, the catalyst forms a new activated complex of a lower activation energy. This means that activation energy becomes lower from the catalyst reaction than that of uncatalyzed reaction. Consequently, the large number of molecules can cross the low activation energy barrier and hence the reaction of rate also increases. In figure 5, the solid lines show the path for catalyst reaction and dotted lines show the path for catalyst reaction. Following points must be noted about the function of a catalyst. Following point must be noted about the function of a catalyst. First, the catalyst does not change del E of the reaction. This is clear from the figure 5 that the addition of a catalyst does not change the energy of a reactant and the product, so that del E remains the same. Although the catalyst speeds up the reaction, but it does not affect the position of equilibrium in case of a reversible reaction. This is because the activation energy for the forward reaction and backward reaction is reduced to the same extent. As a result, the increase in a rate of a forward and backward reaction is same, and hence the position of equilibrium remains unaffected. However, catalysts increase both the rate, hence the equilibrium is attained earlier. Exposure to the radiation. In some cases, the rate of a reaction is considered increased by the use of a certain radiation. The photon of this reaction possesses sufficient energy to break certain break in a reactant. For example, rate of a hydrogen and chlorine take place very slowly in the absence of a light. Hence, in the presence of light, the reaction takes place very rapidly. Nature of a solvent. Nature of solvent also affects the rate of a reaction. These effects can studied under the following properties of a solvent. First, magnitude of a dielectric constant of a solvent. Second, polarity of a solvent. Third, effect of a solvation. First, magnitude of a dielectric constant of a solvent. In case of an ionic reaction in a solution, the inter-ionic forces are largely affected by the dielectric constant of a solvent. Therefore, the rate of a reaction is found to be vary with the dielectric constant of a solvent according to the following equation. Log K is equal to A minus B by D, where D is the dielectric constant of a solvent and A and B are the constant for two ionic in solution. According to above equation, the logarithmic of a rate constant should vary linearly with reciprocal of a dielectric constant of a solvent at a particular temperature. Therefore, a plot of a log K with 1 by D show give a straight line. Figure 6. Second, polarity of a solvent. For a reaction between polar reactant, the rate of reaction is greatly affected by the polarity of a solvent. It has been observed that a polar solvent increases the rate of reaction in which the product form is more planar than reactant and decreases the reaction rate. If a product form is less polar than the reactant, for example, formation of a quaternary ammonium sulfate formed by reaction between trimethylamine and ethyl iodide is favored by the increased polarity of a solvent as shown in table 1. This is because the product quaternary ammonium salt is more polar than either of a reactant triethylamine and ethyl iodide. On the other hand, the reaction between acetic anhydride and ethyl alcohol give rise to the product ethyl acetate. Formed here is less polar than a reactant, ethyl alcohol and acetic anhydride. So the solvent which favor the formation of quaternary ammonium salt trend to slow down the esterification reaction, in which the product are of a lesser polarity than the reactant. The order of polarity of a solvent in table 1 is nitrobenzene, benzene, hexane. If the reactant and the product do not differ much in polarity, then the effect of a polar of a solvent is insignificant on the rate of reaction. For example, in decomposition of a nitrogen pentoxide to form nitrogen trioxide and oxygen, the rate reaction is almost unaffected by the polarity of a solvent because the reaction and the product are of almost same polarity. This fact is clear from the data given in table 2. Influence of a solution. The rate of reaction is largely affected by the degree of solution of a reactant and the activation energy. The solution of a reactant or activation complex lower than the potential energy by an amount equal to a solution energy. Three different cases of a solution are shown in figure 7. Case 1. The reactant are appreciable solvent but the activation complex is not. In this situation, the potential energy of a reactant is lower due to solution. Figure 7. As a result, the energy of activation energy for a reaction increase and the rate of reaction decrease. Case 2. The activation energy is complex between the rate of reactant or not. In case the potential energy of activation energy decrease due to solvation. Figure 7b. The energy of activation energy of the reaction decrease, consequently the rate of reaction increase. Case 3. Both the reactant and the activation complex are solvated. In such a situation, the potential energy of a reactant and the activation complex due to solvation, figure 7c, the net result is increase in activation energy of a reaction and hence the reaction will take slowly than in a solvent in which the reactant and activation energy are not solvated. Concentration depend on a reaction rate of a mass action. When a chemical reaction proceeds, the reactant gets converted into product. As a result, the concentration of a reactant decreases while that of a product increases. The quantitative relationship between the rate of a reaction and the molar concentration of a reacting substance is known as law of mass action. According to this law, at a given temperature, the rate of a chemical reaction is directly proportional to the product of a molar concentration of a reactant. Consider a simple reaction. A plus coefficient of B give product. According to law of mass action, rate of reaction may be written as rate is equal to K A ki power A B ki power B, where A and B are a molar concentration of a reactant. K is a constant of a proportionality and is called the rate constant or velocity constant. Now, if the concentration of each of a reactant is unity such that A is equal to B is equal to 1 mole per liter, then substituting the value in above expression, we get rate of reaction is equal to K into 1 into 1 is equal to K. Thus, the rate constant of a reaction at a given temperature may be defined as the rate of a reaction when the concentration of each of a reactant is unity. Hence, the rate constant is also called specific reaction rate. rate law expression. The actual dependence of a rate on a concentration of a reactant or a product is measured experimentally. For example, in reaction, coefficient of A plus coefficient of B give product. The dependence of a rate of a reaction on a concentration is found to be rate is equal to K A ki power A ki power P B ki power Q, where P and Q are experimentally determined power of concentration of a reactant A and B respectively, on which the reaction rate depends. The power P and Q may or may not be equal to a coefficient A and B in a reaction. The expression 2 in the rate law or a rate equation. Rate law differ from the law of mass action. The rate law gives experimentally observation depend of rate on the concentration of a reactant. The power of concentration of a reactant in rate law expressed may or may not be same as the coefficient of a concentration in the balanced chemical equation. In above given reaction, according to rate law of mass action, give rate is equal to K A ki power A B ki power B. The rate law expression is rate is equal to K into A ki power P B ki power Q. Order of a reaction. Order of a reaction is defined as the sum of a power to which the concentration term are raised in the rate law equation to express the observed rate of a reaction. Thus, if the rate of a reaction A plus coefficient of B give product is given by the rate law as rate is equal to minus dx by dt is equal to K A ki power Q plus B ki power P. Then order of a reaction n is equal to P plus Q. If n is equal to 1, the reaction is said to be first ordered. If n is equal to 2, the rate is said to be second order, and so on. Some common example of a reaction of a different order are given below. First, reaction of a first order. Decomposition of N2O5. N2O5 change into NO2 plus oxygen. Rate is equal to K into N2O5. Second, reaction of a second order. Decomposition of NO2 and 2NO2 plus fluorine give NO2F. Reaction of a third order. Reaction between NO and Cl2. Second, reaction between NO and O2. Reaction of a fractional order. Decomposition of acetaldehyde. Second, reaction between hydrogen and bromine. Zero order reaction. A number of reactions are known in which the rate of reaction is depending of a concentration of a reactant. For example, the decomposition of ammonia at a surface of a metal like platinum. The rate of a reaction is independent of a concentration of ammonia such that rate is equal to K into ammonia power 0. Rate is equal to K order 0. Thus, a reaction is said to be zero order if its rate of is independent of a concentration of a reactant. In such reaction, the rate of a reaction remains constant throughout. The amount of substance reacted is proportional to the time. Zero order reactions are relatively uncommon. Many photochemical reactions and heterogeneous reactions have been found to be a zero order. Photochemical reaction. The reaction which take place in the presence of a light are called photochemical reaction. Many photochemical reactions, example formation of HCl from H2 and Cl2, are example of a zero order reaction. The kinetics of a combination reaction of H2 and Cl2 in the presence of light can be studied in the laboratory by a chemical experiment. A test tube filled with a mixture of H2 and Cl2 gas is inverted in a through containing water. The setup is exposed to sunlight and the photochemical reaction takes place. The HCl formed is soluble in water. As a result, level of water rise in the test tube. It is found that after some time the amount of H2 and Cl2 decrease, but their concentration remain unchanged. This proves that photochemical reaction between H2 and Cl2 is a zero order reaction. Heterogeneous reaction. Zero order reaction are found in heterogeneous system. A heterogeneous system, the reactant, product and the catalyst are present in a different phase. The well-known example of heterogeneous reaction with zero order are: first, decomposition of hydrogen iodide on the surface of gold. Second, decomposition of ammonia on a surface of a metal like palladium, molybdenum, tungsten at high temperature. In such reaction, the reactant is absorbed on the surface of a catalyst where it is covered into a product. At low concentration, the reactant is first order, but when the surface of a catalyst is fully covered with reactant, the reaction becomes zero order. On increasing the concentration of reactant, the reaction rate does not change. In other words, the rate of reaction come independent of a concentration and therefore become zero order. For example, amyl the decomposition of NH3 on the surface of a finely divided platinum is a first order when the pressure of NH3 in a system is low. However, at high pressure, when the surface of a catalyst becomes fully covered with a layer of NH3 molecules, the reaction becomes zero order. Some enzyme catalyst reactions are also zero order reaction. Integrated rate law expression. When we have learned that the instantaneous rate of a reaction is given by differential rate law equation. For example, for a journal reaction, coefficient of A plus coefficient of B give O product. The differential rate law equation is dx by dt is equal to k into a की power a plus b की power b. The differential form of rate law is transformed to integrated form of a rate law equation. The integrated rate equation for a different order reaction can be derived as given below. Zero order reaction. In a zero order reaction, the rate of independent of a concentration of reaction consider a general zero order reaction. A change into product. Let A be the concentration of a reactant and K is the constant for a zero order reaction. Since the rate of a reaction is independent of a concentration of a rate A, thus rate of reaction is equal to minus dA by dt is equal to K into A की power 0 is equal to K. This is the differential rate equation. Rearranging above equation, we get minus dA is equal to k dt. Integrated above equation, we get integration minus a is equal to kt plus I, where I is the constant of integration. The value of I can be calculated from the initial concentration. Let the initial concentration of A be A naught at a time t. Then above equation become I is equal to minus A naught. Substitute the value of I in equation second, we get minus A is equal to kt minus A naught. Kt is equal to A naught minus A. K is equal to 1 by T A naught minus A. This is the integrated rate expression for a zero order reaction. The rate constant K can be calculated if we know the concentration of A at any time T and the initial concentration A naught. Alternate the rate constant K can be calculated as follows. Let the initial concentration of A be A mole per liter and let X mole of a reaction converted into product in a time t. Then concentration of A left after time t be A minus X mole per liter such that initial concentration A product 0. Concentration at time t A minus X product X. A naught is equal to A is equal to A minus X. This equation 3 become kt is equal to x, k is equal to x by t or x is equal to kd. This is a general equation for a zero order reaction. It shows that for a zero order reaction, the amount of substance react is proportional to a time. Important characteristic of a zero order reaction. The integrated rate law equation for a zero order reaction are kt is equal to a naught minus a is equal to minus kt plus a naught. Third, k is equal to 1 by t a naught minus a. It can be seen from equation second that if we plot a graph between a against t, we get a straight line with slope minus k and intercept equal to a naught. The differential rate equation for a zero order is the rate is equal to k a की power 0 is equal to k. It is clear from the equation that rate of a zero order reaction is independent of a concentration of a reactant. Therefore, a plot of a reaction of a versus concentration of a reaction will be straight line parallel to concentration action. Second, half-life of a zero order reaction. Half-life T half of a reaction is the time required for the concentration of reactant to decrease to half of initial value, such that T is equal to T half, A is equal to A naught by 2. Substituting the value in integrated rate equation, T is equal to 1 by K A naught minus A. T half is equal to 1 by K is equal into A naught minus A naught by 2. T half is equal to A naught by 2K. Thus, the half value of a zero order reaction is directly proportional to initial concentration of a reactant. That means if the initial concentration of reactant is made double, the time required for a reaction to be half complete is also doubled, and so on. Unit of a rate constant K. The rate equation for a zero order is K is equal to 1 by T A minus A naught. K is equal to 1 by time concentration. Mole is equal to mole per liter divided by time. Mole per liter per time. Kinetics of a first order reaction. A reaction is said to be first order if the rate depends upon a concentration variable only. Consider a first order reaction A change into product if the initial product of A is a mole per liter, and let X of a reactant get change into product in time t. Then the concentration of A after time t is A minus X mole per liter. Then according to law of mass action, the rate of a reactant directly proportional to A dx by dt directly proportional to a minus x is equal to k into a minus x, where k is the rate constant or a specific reaction rate for a first order reaction. Equation first is the differential rate equation. Rearranging above equation, we get dx by a minus x is equal to k dt. Integrate this equation, we can write minus log a minus x is equal to kt plus I, where I is the constant of integration at the start of a reaction such that at t is equal to 0, x is equal to 0. Substituting these values in equation second, we get minus log a is equal to I. Substituting the value of I in equation second, we have minus log a minus x is equal to kt minus log a. Kt is equal to log a minus x is equal to log a divided by a minus x. K is equal to 1 by t log a divided by a minus x. K is equal to 2.303 divided by t log a divided by a minus x. Equation 4 may also be written in alternate form as follows. If the initial concentration of A is C naught at t is equal to 0, and at time t of a concentration A is Ct, then A is equal to C naught and A minus X is equal to Ct. In equation 4, we get K is equal to 2.303 divided by my T log C naught divided by my Ct. Similar equation 3 may be written as Kt is equal to log C naught by T. Equation 6 may be written in exponential form such that log C naught divided by Ct is equal to Kt log Ct divided by C naught is equal to minus Kt. Taking antilog of both sides, Ct divided by C naught is equal to e की power minus Kt. Ct is equal to C naught e की power minus Kt. This is very useful form of integration first order rate equation, as it directly given the concentration of a reacting species at any time Ct. If the initial concentration C naught and the rate of a constant K are known. Important characteristic of a first order reaction. A first order reaction must obey any of the following rate equation. K is equal to 2.303 divided by K log A divided by A minus X. Second, K is equal to 2.303 divided by T log C naught divided by Ct. Third, Ct is equal to C naught e की power minus Kt. Second, in a rate of a first order reaction, the rate equation Ct is equal to C naught e की power minus Kt means that the reaction never proceeds to complete because Ct can become zero only at infinite temperature T. First order reaction can be tested by following method. A substitution method. All the reaction of a first order obey the following equation. K is equal to 2.303 divided by T log A divided by A minus X. 2.303 divided by T log C naught divided by Ct. Starting with a known concentration A or a C naught, the concentration of reactant A minus X or a Ct is not at different interval of a time. The value of a concentration A minus X or a Ct at different interval are substituting in above equation. If the value of a K come out of a constant, then the reaction is of a first order. By graphical method, equation 5 may be written as Kt divided by 2.303 log C naught divided by Ct. Kt divided by 2.303 is equal to log C naught minus log Ct. Log Ct is equal to minus K divided by 2.303 T plus log C naught. This equation is comparable to the equation of a straight line y is equal to mx plus c. When a graph is plotted between log Ct and time t at variable interval of a time, a straight line is obtained, showing that the reaction of is the first order. This is shown in figure 10. The slope of a line is equal to minus k by 2.303. For this rate constant k can be calculated. Alternatively, if we write the equation 8 as log C naught divided by Ct is equal to Kt divided by 2.303, the slope of a log C naught divided by Ct versus T will give a straight line with the slope is equal to K divided by 2.303. Calculation of a rate constant when initial concentration is not known. Integrated rate equation can be used to test a first order reaction when the initial concentration of a reactant is not known. In such cases, the initial concentration term A is eliminated. This is done as follows. Let the concentration of reactant at time t1 is equal to A minus x1. The concentration of reactant at time t2 is equal to A minus x2. The integration rate equation can be calculated as K is equal to 2.303 divided by T1 log A divided by A minus x1. K is equal to 2.303 divided by T2 log A divided by A minus x2. Subtract equation 9 from equation 10, we get K divided by 2.303 T2 minus T1 is equal to minus log A minus x2 plus log A minus x1. Log A minus x1 divided by A minus x2. K is equal to 2.303 divided by K2 minus T2 minus T1 log A minus x1 divided by A minus x2. If Ct1 and Ct2 are the concentration of reactant at time interval T1 and T2, then the equation 11 can be expressed as K is equal to 2.303 divided by T2 minus T1 is log Ct1 by Ct2. If a plot of a log A minus x1 divided by A minus x2 or a log Ct1 divided by Ct2 versus T2 minus T1 gives a straight line passing through a region with slope K divided by 2.303 is obtained, then the reaction is of a first order. Fifth, half-life period of a first order reaction. Half-life of a reactant is time required for the concentration of reactant to reduce of half of its original value. The integration rate equation is T is equal to 2.303 divided by K log A divided by A minus X. At T is equal to T half of a reactant has reacted such that X is equal to A by 2. Writing half-life time period as T half and substituting the value of X in equation 12, we get T half is equal to 2.303 divided by K log A divided by A minus A by 2. Log 3.30 divided by K log 2, T half is equal to 0.693 divided by K. The initial concentration term it does not appear in equation. Thus, half-life of a first order reaction is independent of the initial concentration of a reactant. Similarly, it can be shown that in a first order reaction, the fraction life period such that T1 by 3 T3 by 2, etc. are also independent of initial concentration of reactant. For example, time required to complete 1 by 3rd of a reaction will be given as x is equal to a by 3, a minus x is equal to a minus a by 3, 2 by 3a. Third is equal to 2.303 divided by k log a divided by 2 by 3a. 2.303 k log 3 by 2. In general, the time required to complete nth fraction of a reaction will be T1 by n is equal to 2.303 divided by k log a divided by a minus a by n. T1 by n is equal to 2.303 k log 1 by 1 minus 1 by n. Fractional life method can be used to determine whether a given reaction is a first order or not. Sixth, Unit of first order rate a constant. The integration rate equation for first order reaction is given. It is clear that K depends upon a ratio of two concentration term and time t. The unit of K expressed in unit of time inverse. Time may be expressed in second, minute, hour according to the unit of K or second inverse, minute inverse, hour inverse respectively. Some example of first order reaction. The first order reaction are broadly divided into two types. First order gas phase reaction. Second, first order reaction take place in solution. The gas phase reaction of a first order are comparatively few. In this reaction, the progress of a reaction may be followed by measuring the volume of a pressure of a gas. Reactant of a reaction may be followed by measuring the volume of a pressure of a gaseous reactant of a product. Whereas the first order reaction taking place in a solution, the concentration of a reactant is measured at a different interval of a time. Kinetics of some common first order reaction is take place in the following discuss. For the sake of simplicity, the example of a first order reaction has divided into three categories. First, decomposition reaction of a first order. Second, first order reaction involving isomeric change. Third, pseudo-unimolecular reaction of first order. Depending upon the quality that can be measured, the concentration term in the integrated rate equation may be placed by quantity like volume, pressure, rotation of a polarized light, etc. First, decomposition reaction of a first order reaction. This reaction involves decomposition reaction in gaseous phase or in a solution. The decomposition reaction, which involves the change in the number of a gaseous molecule, the concentration term in equation K is equal to 2.303 divided by K T log A divided by A minus X, are replaced by pressure or a volume term. Few decomposition reaction of first order are discussed ahead. Decomposition of nitropentoxide. Nitrogen pentoxide is a volatile solid which decompose in a gaseous form or in its solution in inert solvent like carbon, tetrachloride, chloroform, etc. The reaction is represented as given. The kinetics of a reaction may be studied in two ways: by measuring the concentration of N2O5 in the solution at different interval of time. Second, by measuring the volume of oxygen produced at different interval of time. In first case, the following rate equation is used: K is equal to 2.303 divided by T log A divided by A minus X. However, in a second case, as both N2O4 and NO2 remain soluble in a solution while oxygen gas escape, thus the volume of oxygen gas collected is measured at different intervals of time. The total volume of oxygen collected at the end of a reaction given a measure of a total concentration N2O5 taken initially, such that A, if Vt is the volume collected at any time and V infinity is the total volume collected at end of a reaction, then it is obvious that V infinity directly proportional to initial concentration of N2O5. Vt directly proportional to amount of N2O5 decomposition. V infinity is equal to A, Vt is equal to X. Substitute for A and X in above equation we get. So both form of a rate equation are used depending upon the quantity measured. Second, decomposition of ammonium nitrate. Ammonium nitrate in aqueous solution decompose at room temperature according to the following reaction. The progress of a reaction is studied by measuring the volume of nitrogen produced at different intervals of time. The rate of reaction is used. K is equal to 2.303 divided by T log V infinity by V infinity minus T. Decomposition of benzene diazonium chloride. Benzene diazonium chloride in its aqueous solution decompose according to the following reaction. The progress of reaction can be studied by measuring the volume of a nitrogen gas collected at different intervals of time. The rate equation for a reaction is K is equal to 2.303 log V infinity divided by V infinity minus Vt, where V infinity is the volume of N2 collected at the end of a reaction and Vt is the volume of N2 at any time t. Fourth, decomposition of hydrogen peroxide. Decomposition of hydrogen peroxide takes place according to the given equation. The reaction is catalyzed by the presence of a finely divided platinum. The progress of a reaction is studied by two methods. First, by measuring the volume of oxygen evolved at different intervals. The rate constant can be calculated using the equation K is equal to 2.303 divided by T log V infinity minus V divided by V infinity minus Vt. Second, by estimating the concentration of H2O2 left at a different interval of titrating H2O2 solution against KMnO4 solution. This can be done by withdrawing small amount of H2O2 solution at regular interval and titrating it against standard KMnO4 solution. The volume of KMnO4 used will be directly proportional to the concentration of hydrogen peroxide left behind at any instant. The volume of KMnO4 used before the starting of a reaction, such that at T is equal to 0 given the initial concentration of H2O2. Thus, it is obvious that before the starting of a reaction at T is equal to 0, the volume of KMnO4 used V is not directly proportional to initial concentration of hydrogen peroxide A. At time t, the volume of KMnO4 used Vt directly proportional to concentration of H2O2 at time A and t, such that A minus X. So the first order reaction equation K is equal to 2.303 divided by T log A divided by A minus X. A directly proportional to V0 and A minus X directly proportional to Vt. Substituting this value in first order equation, we get 2.303 divided by T log V0 divided by Vt. The decomposition of hydrogen peroxide obey the rate equation and is found to be first order. Fifth, thermal decomposition of azoisopropane. Azoisopropane decomposes on heating to form hexane and nitrogen according to the given equation. It is a homogeneous gaseous reaction because all the reactant and product are in a gaseous state. Therefore, the progress of a reaction can be followed by measuring the pressure of a reaction measured at different intervals of time. At the start of a reaction, the initial pressure Pi of a reaction mixture is proportional to the initial concentration of azoisopropane A. such that Pi is directly proportional to A. For every molecule of azoisopropane that decompose 1 mole of nitrogen, 1 mole of hexane are produced. As a result, the pressure of a reaction measured increase with the time. At any time t, the total pressure Pt is the sum of a partial pressure of azoisopropane Pa, nitrogen and hexane at instant. Thus, Pt is equal to Pa plus Pn2 plus P hexane. At a given constant T, let P be the decrease in pressure of azoisopropane, then the pressure of each of N2 and hexane increase by an amount P. Thus, at any instant T, the pressure of azoisopropane Pa is equal to Pi minus P. Pressure of nitrogen P, pressure of hexane P. Substituting this value, we get P is equal to Pt minus Pi. But the decrease in pressure of azoisopropane is proportional to the amount of azoisopropane decomposition X, such that X proportional to P. Comparing result 4th and 5th, we get X is directly proportional to Pt minus Pi. From equation first, we get A directly proportional to Pi. Substituting the value of A and A minus X in a first order reaction, we get where Pi is the initial pressure and Pt is the pressure at a reaction at a time t. First order reaction involving isomeric change. Isomeric conversion of a normal chloroacetylene into parachloroacetylene is an example of a first order reaction. The isomerization takes place in acidic medium as follows. The isomerization reaction occurs when normal chloroacetylene is treated with a Ki solution of acidic medium. The study of a kinematic of a reaction is based upon the fact that only normal chloroacetylene react with Ki in acidic medium to liberate iodine, whereas parachloroacetylene does not liberate iodine. Normal chloroacetylene react as follows. As non-solution of a reaction mixture withdraw at different intervals and the iodine liberate is measured by titrating against a standard solution of a sodium thiosulfate using stars as indicator. The volume of a thio solution used at T is equal to 0 is proportional to the amount of I to liberate, which is in turn proportional to the initial concentration A of a normal chloroacetylene, such that A directly proportional to N naught. The volume of a hypo solution used at time t proportional to the amount of I to liberate, which is in turn depend upon the concentration of a nitrogen chloroacetylene lead at the time t, such that A minus X. Thus, A minus X directly proportional to Vt. Substituting this value in a first order reaction, we get the equation takes the form K is equal to 2.303 T log V naught divided by Vt. Pseudo-order reaction. These are reactions which are not unimolecular, yet they get obey first order equation. Some example of such reaction are: first, hydrolysis of ethyl acetate; second, inversion of sugar cane. In this reaction, there are more than one reactant, but the rate of reaction depends on a concentration of only one of a reactant. Consider a general equation: A plus B change into product. The molecularity of a reaction is 2, so it is a bimolecular reaction. However, when one of a reactant is present in a large excess, then its concentration remains particularly constant due to the reaction. Suppose the reactant B is present in excess and its concentration remains physically unchanged. Under such condition, we can write rate is equal to K naught A, where K naught is equal to K into concentration of B. Thus, the reaction appear to be second order but follow first order reaction. Thus, the reaction which appear to be higher order but actually follow first order reaction are called pseudo first order reaction. Consider the hydrolysis of ethylene acetate. The molecularity of a reaction is 2, so it is a bimolecular reaction. The concentration of ethyl acetate changes during reaction, while water is present in higher concentration, and thus its concentration remains practically constant. Therefore, the rate of a reaction depends only on a concentration of ethyl acetate, and hence it is the first order reaction. Thus, the reaction appear to be a second order but follow the first order kinetics. That the reaction which appear to be higher order but actually follow first order kinetics are called pseudo first order reaction. Kinetics of a second order reaction. A reaction is said to be second order if its rate depend upon two concentration terms when may be or may not be same. Therefore, there are two types of a second order reaction. First, reaction involving only one type of a reactant. Reaction involving two types of a reactant. In such reaction, the concentration term to be different to reactant. Consider a general equation: A plus B change into product. The constant K is the term as a rate constant for a second order reaction. The integrated rate equation for these two types of a second order reaction are derived as: first, rate equation for a reaction involving one type of a reactant. Consider a journal second order reaction 2A change into product. Let initial concentration A mole per liter decrease in concentration of at any time t x mole per liter, concentration of A at time t A minus x mole per liter. According to law of mass action, the rate of a reaction directly proportional to A ka square. dx by dt directly proportional to A minus x ka whole square is equal to k into A minus x ka square, where k is the rate constant for a second order reaction. Equation first is a differential rate equation. Rearranging above equation we get integrated this equation we can write 1 by A minus x is equal to kt plus I, where I is the constant of integration at the start of a reaction at t is equal to 0, x is equal to 0. Substituting this value in equation we get 1 by A is equal to I. Put the value of I, we get kt is equal to 1 by A minus x minus 1 by A. Equation 3 may also be written in alternate form. If the initial concentration of A is C naught at t is equal to 0 and at time t the concentration of A is Ct. Substituting equation 4th and 5th we get A minus x minus A is equal to Ct minus C naught minus x is equal to Ct minus C naught. Putting the value of A minus x from the equation 4th, 5th, 6th into equation 3 we get k is equal to 1 by t into 1 by Ct minus 1 by C naught. This is useful for a second order equation as we are directly calculated the concentration of reactant species at any time t if the initial concentration C naught and the rate constant K are known. Second, rate equation for a second reaction involving two different reactant. Consider a general second order reaction A plus B change into product. Two possibility can be raised. When both reactant A and B have same initial concentration, say A mole per liter, then the rate of reaction will be same of as equation 3. However, when the initial concentration of A and B are different, then the rate equation is obtained as followed. Suppose the initial concentration A is equal to mole per liter. The initial concentration of B mole per liter. At any time t, x mole per liter of A and x mole per liter of B reactant to be produce the product. The concentration of A at any time t A minus x, concentration of B at any time t B minus x mole per liter. According to law of mass action, rate of reaction directly proportional to concentration of A into concentration of B, where K is the constant for a second order reaction. Rearranging equation we can write. Resolve the left hand side term into partial fraction. Integrating this equation we can write 1 by A minus B log A minus x divided by B minus x is equal to kt plus I, where I is the constant of integration at the starting of a reaction at t is equal to 0, x is equal to 0. 1 by A minus B log A by B is equal to I. Putting the value of I in equation 10 we get k is equal to 2.303 divided by t into A minus B log B into A minus x divided by A into B minus x. Alternate equation 12 may be written in term of a concentration directly. Let initial concentration A is equal to C naught A. The concentration at time t, CTA. Similarly, concentration of B at time t is equal to 0, C naught. Concentration of B at time t, CTB. K is equal to 2.303 divided by T into C naught A minus C naught B log C naught B into CTA divided by C naught A into CTB. Equation 13 get modified if one of a reactant is present in excess. Suppose reactant A is present in excess, then A will be very large as compared to B, so that A minus B similarly mostly equal to A. A minus x directly proportional to A. Substituting the value of A minus B and A minus x in equation 12, we get K into A is equal to 2.303 divided by T log B divided by B minus x. As A is taken in excess, therefore it will remain almost constant. Therefore, equation 14 can be written as K dash is equal to K into A is equal to constant. Equation 15 is an equation of a rate constant for a first order reaction. The bimolecular reaction in which one of the reactant is taken in excess called pseudo-molecular reaction. The reaction follow first order kinetics. Important characteristic of a second order reaction. A second order reaction may be obey any of a following rate equation. K is equal to 1 by T into x divided by A into A minus x. Second, order reaction can be tested by following methods. Substitution method, graphical method, etc. Substituting method. In this method, the value of A, B and the amount of reactant substance X at different interval time are substituted in a rate equation and the value of a rate constant is calculated. The constancy in the value of a K indicate the second order reaction. Graphical method. Second order reaction equation K is equal to 1 by T into 1 by C naught minus 1 by Ct may be written as Kt is equal to 1 by Ct minus C naught. This is an equation of a straight line when a graph is plotted between 1 by Ct and the time t at various interval of a time. A straight line is obtained showing that the reaction is of first order. The slope of a line is equal to K, which is directly given the value of a rate constant. When the rate equation involving two different reactants, then the equation is used. Equation 13 can be written as shown. This is the equation comparable to equation of a straight line y is equal to mx plus c. Plotted against time t, a straight line is obtained. The slope of a line is k into c naught a minus c naught b divided by 2.303. Hence, the value of a rate constant k can be calculated. Equation 3 and 12 can also be used for calculating k by graphical method. Equation 3 can be rearranged as given. The plot of 1 by a minus x must be a straight line with the slope equal to k. Simply, equation 14 can be written as in follows: log a minus x divided by b minus x is equal to k into a minus b divided by 2.303 into t plus log a by b. Thus, the plot of a log a minus b divided by b minus a versus time t must be straight line having slope equal to k into a minus b divided by 2.303. Thus, the second order reaction rate constant k can be elevated as 3 half-life period of a second order reaction. For a simple second order reaction to a change into product, the rate equation is k is equal to 1 by t into x divided by a into a minus x, where a is the initial concentration, a minus x is the concentration at any time t. Half-life t half is the time when initial concentration reduced to half such that x is equal to a by 2. Substituting this value in above equation, we get t half is directly proportional to 1 by a. Thus, the half-life time period of a second order reaction is inversely proportional to initial concentration of a reactant. Similarly, it can shown that the time required for completion of any factor of a second order reaction is inversely proportional to the initial concentration. Let us calculate the time taken for 2/3 of a reaction to be completed. That is t is equal to t into 2 by 3, where x is equal to 2 by 3a. Substituting this value in a rate equation, we get 1 by k into 1 by 2a. The fractional life method can be used to test whether a given reaction is of second order or not. Unit of a second order rate constant is liter, mole inverse, time inverse. Thus, the unit of a k for a second order reaction are liter, mole inverse, time inverse. Equation 3 and 12 can also be used for calculating k by graphical method. Equation 3 can be rearranged as 1 by a minus x is equal to kt plus 1 by a. Thus, the slope of 1 by a minus x must be a straight line. ये तो पढ़ लिया था. Some example of a second order reaction. Second order reaction in a gaseous phase. Second order reaction in a solution phase. Gaseous phase. Many homogeneous reaction in a gaseous phase follow second order reaction kinetics. These are a general decomposition reaction. Example: dissociation of ozone, nitrous oxide, acetanilide, chloromethane monoxide. Second order reaction in solution. The reaction belonging to the categories are saponification of ester with sodium hydroxide, conversion of ammonium cyanate into urea, benzoin condensation, hydrolysis of amide, etc. Kinematics of some reaction are discussed below. First, thermal decomposition of acetanilide. Thermal decomposition of acetaldehyde in vapor phase taken place as per the equation. It is seen that reaction follow first order kinetics, but it is experimentally found to be a second order. Therefore, it is expressed as it is a homogeneous gaseous reaction. Therefore, the progress of a reaction can be followed by measuring the pressure of a reaction measured at different interval of a time. The reaction involved decomposition of acetaldehyde into two gaseous molecules, ammonia and methane. Carbon monoxide and methane. So the reaction is accompanied by the increase in number of mole of the gaseous product. Hence the pressure of a reaction mixture increase as the reaction proceed. At the starting of a reaction, the initial pressure of a reaction measured is proportional to the initial concentration of acetaldehyde, such that Pix into A. At any time t, the total pressure of a reaction Pt is the sum of a partial pressure of a aldehyde, methane, and carbon monoxide. At any time t, let P be decrease in a pressure of acetaldehyde, then the pressure of each of methane and carbon monoxide increase by amount P. Therefore, at any time t, the pressure of acetaldehyde is equal to Pi minus P. Pressure of methane P, pressure of carbon monoxide P. Substituting these values are in equation 2, we get P is equal to Pt minus Pi. But the decrease in pressure of acetaldehyde is proportional to the amount of acetaldehyde decomposition, X. Comparing expression 4 and 5, we can write X directly proportional to Pt minus Pi. A directly proportional to Pi, A minus X directly proportional to 2Pi minus 2Pt. Substituting this value A x and A minus x in a second order rate equation, we get K is equal to 1 by T into Pt minus Pi divided by Pi into 2Pi minus Pt. Second, saponification of ester. The reaction of ester with the sodium hydroxide is called hydrolysis or saponification of ester. The reaction between ethyl acetate and sodium hydroxide is of second order and take place as follows. The reaction is carried out in a vessel at a constant temperature by taking an equimolar amount of ethyl acetate and sodium hydroxide. As sodium hydroxide is one of a reactant, its concentration decreases as the reaction proceeds. The concentration of NaOH at any time t can be found to be titrated the reaction mixture against standard acid. The amount of unfused ammonium hydroxide is equal to the unreacted ester because the initial concentration of both is equal and equal number of mole of each is reacting. Thus, at time start of a reaction such that at t is equal to 0, the volume of a standard acid used Vt directly proportional to concentration of ammonia. At any time t, the volume of a standard acid used Vt directly proportional to concentration of ammonia at that time such that A minus X. Subtracting expression second from first, we get X directly proportional to Vi minus Vt. Substituting value of A minus X into second order reaction, K is equal to 1 by T Vt minus Vi divided by Vi into Vt. Kinetics of a third order reaction. A reaction is said to be third order if rate depend upon concentration of three reactant may or may not be same. They are of three types. First, reaction involving three different molecules of a different reactant. Second, reaction involve two different reactant as given. Third, reaction involving three molecules of a single reactant. The constant K is called a rate constant for a third order reaction. The simple case of a third order reaction is 3A change into product. The integrated rate equation for such a reaction is derived as initial concentration A mole per liter at any time t x, concentration of A at any time t A minus x. Apply law of mass action. The rate of equation directly proportional to concentration of A का cube, where K is the rate constant for a third order reaction. Express 1 can be written as dx divided by A minus x का cube is equal to K dt. Integrating this equation, we can write 1 by 2 A minus x का square is equal to kt plus I, where I is the constant of integration at starting of a reaction such that t is equal to 0, x is equal to 0. Substituting this value in equation second, we get 1 by 2 A square is equal to I. Put the value of I in equation second, we get kt is equal to 1 by 2t into x into 2a minus x divided by a का square into a minus x का whole square. Equation 3 may be written in alternate form. If the initial concentration of A is A0 at t is equal to 0 and at time t the concentration of A is Ct. Putting the value of A minus x to A minus x from equation 4, 5, 6, 7 into equation 3, we get K is equal to 1 by 2t into C0 square minus Ct square divided by C0 square into Ct square. Important characteristic of a third order reaction. A third order reaction may obey rate equation 3 or 8. This can be tested by substituting method or graphical method. Half lifetime period for a reaction. Half lifetime period of reaction may be defined as the time during which the concentration of a reactant is reduced to half of its original value. It may also be defined as the time required for completion of a half of the reaction. It generally denoted as T half. The half lifetime period for a reaction of zero order, first order, second order, or third order has been calculated during the earlier discuss. A brief comparison of all these is summarized as follows. For a zero order reaction, T half directly proportional to A. It is obvious that from a zero order reaction, the half life period is directly proportional to initial concentration. Second, for a first order reaction, K is equal to 2.303 divided by T log A divided by A minus X, or T is equal to 2.303 divided by K log in A divided by A minus X. At T is equal to T half, X is equal to A by 2. T half is equal to 0.3693 divided by K. It is clear from the equation that for a first order reaction, the half lifetime period is independent of its initial concentration. For a second order reaction, T is equal to 1 by K into X divided by A into A minus X. T is equal to T half, X is equal to A by 2. T half is inversely proportional to A. For third order reaction, T half inversely proportional to A ka square, such that half life period of a third order reaction is inversely proportional to square of initial concentration of reactant. In general form of a reaction of an nth order, the expression for half lifetime period is T half directly inversely proportional to A the power n minus 1. Molecularity of a reaction. According to the collision theory, for a chemical reaction to occur, the reacting molecule must collide with each other. The number of reacting species which collide stimulously to bring about a chemical reaction is called molecularity of a reaction. The molecularity of a reaction can be 1, 2, 3. In case of elementary reaction, such that the reaction which involves single step, the molecularity is simple, the sum of a molecule of a reactant as in the balanced chemical equation. Following are some examples of molecularity of elementary reaction. First, decomposition of hydrogen peroxide. Decomposition of hydrogen peroxide involves single species which form product. Hence, it is a unimolecular reaction and its molecularity is 1. Second, dissociation of hydrogen iodide is a bimolecular reaction because two molecules collide to bring about the reaction. Hence, its molecularity is 2. The reaction of nitric oxide and oxygen is a trimolecular reaction because it involves collision of 3 reacting molecules. In similar way, we can expect a reaction which involves the collision of 4 or more molecules. However, it has been observed that reaction involves 3 or more molecules are uncommon. The reason of that is the chance of a stimulation collision of 3 or more molecules are very small. In case of complex reaction, the balance equation involves large number of reacting species is usually more than 3. In case of complex reaction, the balance equation involves large than number of reacting species, but the chance of a stimulation collision of such large number of species is very rare. Such type of reaction takes place through 2 or more consecutive steps. In cases of a multi-step reaction, the slowest step is a rate determining step. The number of reacting species which occur in a slowest step or the rate determining step is called the molecularity of a complex reaction. It is clear from above reaction that molecularity is always a whole number such that 1, 2, 3, etc. It can have fractional value, whereas the order of a reaction can have fractional value also. Mechanism and the rate law. We have learned that the complex reaction takes place through a sequence of 2 or more than consecutive steps. Each step is an elementary step and involves the stimulation collision of 2 or 3 species. The detailed description of various steps by which the reactant change into product is called mechanism of a reaction. The steps which contribute to the overall reaction are called elementary reaction. In case of multi-step reaction, each elementary step occurs at a different rate. Such steps are fast while others are slow. The step which occur much more slowly than other steps is the rate controlling or rate determining step in the proposed mechanism. This slowest step has occurred. The other step will take place to form the product. Thus, the slowest step determining the rate of a reaction. Thus, the experimentally observed expression which involves the rate molecule on which the rate of a reaction actually depends is called the rate law equation. It is illustrated from the following example. First, reaction of first order, the thermal decomposition of dinitrogen pentoxide. It has been experimentally found that if the reaction were to be take place by collision of two N2O5 molecule as indicated by the balance equation, it would be second order reaction, but it observed rate law equation that it is a first order reaction. This means it is a complex reaction or proceed by two or more steps. Second, bromide of acetone. Acetone is bromide in dilute aqueous solution according to the following reaction. It is observed experimentally that the rate of reaction depending only on a concentration of acetone. Hence, the rate determining step must involve only acetone molecule. This proposed mechanism step 1, step 2, thus it is a unimolecular reaction of a first order. Reaction of a second order, reaction between N2O and F2 to form N2OF. Experimentally observed indicate that the rate determining step indicates the reaction between N2O and F2 only. Thus, the probability mechanism is N2 NO2 plus F2 change into NO2F plus F slow step. Second step, N2 plus F change into NO2F fast step. This has a bimolecular reaction of a second order. Second, decomposition of hydrogen peroxide. The decomposition of hydrogen peroxide is catalyzed by a iodine ion in an alkali medium. It has been experimentally found that the rate determining step involves one molecule of H2O2 and iodine. This means that it is a complex reaction. The probability mechanism of reaction is third, oxidation of hydrogen bromide with oxygen. It has been experimentally found that hence the reaction is second order and probability mechanism is reaction of a third order. First, reducing of a nitrogen oxide with hydrogen. The rate law equation is found to be rate directly proportional to concentration of NO square into concentration of H2. The rate law expression suggests that it is a complex reaction. It is believed to proceed by the following mechanism. Since the first step is slowed and rate determining, the rate is equal to K into concentration of N2 into H2. Second, oxidation of hydrogen bromide by hydrogen peroxide. The reaction occurs in aqueous medium as follows. In aqueous medium, equation can be written as: it has been found experimentally that rate is equal to K into concentration of hydrogen peroxide into concentration of H positive ion into concentration of Br negative ion. Hence, the above reaction is a trimolecular and of a third order. It is obvious that the rate determining step should involve one molecule of H2O2, one molecule of H positive ion, and one molecule of Br negative ion. Therefore, the proposed mechanism is given as: difference between molecularity and order of a reaction. Molecularity. In a simple or elementary reaction, molecularity is the number of molecules of a reactant as present in a balanced chemical equation, where in a complex reaction, it is equal to number of molecules present in the rate law equation. Order. Order is the sum of a power of the concentration term in the rate law expression. Molecularity is a theoretical concept. Order of a reaction is determined experimentally. Molecularity can have integral value only such that it is always a whole number. Order of a reaction need not to be whole number such that it can have fractional value also. Molecularity of a reaction cannot be zero. Order of a reaction can be zero. For a simple reaction, the molecularity can be obtained from stoichiometric coefficient of a chemical equation. Order of even a simple reaction may not be equal to a number of reacting molecule present in a balanced chemical equation. Method for determining the order of a reaction. There are the number of methods for determining rate law of or order of a reaction. The following methods are commonly used. First, use of integrated rate equation. In this method, the initial concentration of reactant and the concentration of one of the product is measured by the sum substitution method. Then one of the following method is used for determining of the order of a reaction. First, substitution method. Second, graphical method. Differential rate equation method. Van 't Hoff differential method. We have discussed that in first order reaction the rate is proportional to one concentration term, and in second order the rate that depend on a two concentration term, and so on. Generally, the rate equation of nth order is proportional to nth power of a concentration. Rate is equal to minus dc by dt is equal to k into c to the power n, where k is the rate constant, c is the concentration of any time t, and n is the order of the reaction. For two differential concentration, we can write R1 is equal to minus dc1 divided by dt is equal to k into c1 to the power n. R2 is equal to minus dc2 divided by dt is equal to k into c2 to the power n. Taking log on both sides of above equation, we get spread equation for 5 from 4, we get log R1 minus log R2 is equal to n log C1 minus n log C2. Thus, the order of a reaction can be calculated using equation 6. The order of a equation reaction n can be calculated if the value of rate R1 and R2 at different concentration C1 and C2 are known. This can be done by any of the following method. The value change in concentration del C of a reactant is measured in a small time interval del T. The value of del C divided by del T is assumed to be constant in a given interval time. Hence, del C divided by del T can be taken equal to dV by dt. Therefore, the value of R such that dC1 divided by dt and R2 such that dC2 by dt at different concentration C1 and C2 can be calculated. Second, in this method, the rate is determined by plotting concentration of a reactant against time. The slope dC1 by dt and dC2 by dt at different concentration at a given time interval is measured by drawing tangent at that point using the value of slope R1 and R2 in equation 6. The order n can be calculated. Half-life period method. This method is also known as fractional change method. Half-life period of a reaction is during the time which the concentration of reactant is reduced to half of its initial. We also know half-life directly proportional to initial concentration for a zero order reaction. Second, half-life is independent of initial concentration for first order. Second, half-life is inversely proportional to initial concentration of a second order. Fourth, half-life is inversely proportional to square of initial concentration for third order. In generally, for an nth order reaction, T half inversely proportional to a to power n minus 1. For two different initial concentration A1 and A2 may be written as T half 1 inversely proportional to A1 to power n minus 1. T half 2 inversely proportional to A2 to power n minus 1. Dividing equation second by equation third, we get T half 1 divided by T half 2 is equal to A2 divided by A1 to power n minus 1. Taking log both sides, we have log T1 half minus log T half 2 is equal to n minus 1 log A minus log A2. Solving for n order reaction, we get n is equal to 1 plus log T half 1 minus log T half 2 divided by A2 minus A1. Substituting the value of two initial concentration A1 and A2 half-life period from the two experimental value of n can be calculated. Oswald isolation method. This method is employed in determining the order of a reaction which involves two or more reactants. This method is based on the principle that the contribution of a reaction taken in excess to order of a reaction can be neglected. In this method, the concentration of all but one of a reactant are taken in excess. Thus, the concentration of those reactants taken in excess will remain almost constant, and the concentration of reactant present in a small amount is varied. The rate of reaction will vary with the concentration of isolation reactant. This helps to predict the order of a reaction with respect to one reactant. In this way, one reactant is isolated from the other and observed. This process is repeated with other reactant one by one, and order with respect to each reactant is determined. The overall order is the sum of all these order. For example, consider the general equation as given. Suppose we isolated A by taking B and C in a large excess and get order of a reactant with respect to A. Similarly, we isolated B by taking A and C in excess, isolated C by taking A and B in excess, and obtained the order with respect to B, C respectively. Overall order of a reaction N is equal to X plus Y plus Z. Theory of chemical kinetics. Effect of temperature on a rate of reactant Arrhenius equation. In 1889, Arrhenius gave the quantitative relationship between temperature and the rate constant, and hence the rate of reaction. The expression is called Arrhenius equation and is written as K is equal to A into e की power minus EA by RT, where A is a constant called a frequency factor, EA is the activation energy, R is the real gas constant, and T is the temperature. The factor E the power minus EA by RT give the fraction of molecule having energy equal to or greater than activation energy. The activation energy represents the minimum energy that reacting molecule must possess before undergoing a reaction. Activation energy EA cannot be measured directly but can be calculated using Arrhenius equation as follows. Taking log on both sides, equation 1 we get log K is equal to log A minus EA by RT. If K1 and K2 are the rate constant for a reaction of a two different temperature T1 and T2 respectively, log K1 is equal to log A minus EA by R T1 and log K2 is equal to log A minus EA by R T2. Subtracting equation 3 from 4 we get log K2 divided by K1 is equal to A8 divided by 2.303 R T2 minus T1 divided by T1 into T2. Thus, knowing the value of a rate constant K1 and K2 for at two different temperature T1 and T2, the value of activation energy can be calculated. Equation 5 can also be used to calculate the rate constant at any time T if the rate constant at any temperature and the value of EA is known as the particular reaction. Alternate, the energy of activation energy EA can be calculated by writing the Arrhenius equation in a form of equation of a straight line. Equation 1 may be written as log K is equal to minus EA by RT plus log A. 2.303 log K is equal to minus EA by RT plus 2.303 log A. This equation is in a form of y is equal to mx plus c. When log K is plotted against 1 by t, we get a straight line in figure 1. The intercept of this line is equal to log A and the slope is equal to minus EA by 2.303 r. Slope is equal to minus EA by 2.303 r. Know the value of the slope and gas constant. Activation energy can be calculated. EA is equal to 2.303 into r into slope. Thank you. The chapter is complete.